Welcome to Chapter 9. We're going to be talking about heat now. And this first section is on something called thermal equilibrium. And it says Part A here, but that's a little deceiving because it's the only part, because really there's only concepts here. All the math should be review, even from like 8th grade. So what we're going to talk about is we're going to relate temperature to kinetic energy of atoms and molecules. And we are going to describe the changes in temperatures of two objects reaching thermal equilibrium. You will also need to be able to identify the various temperature scales and convert from one scale to another. So what is temperature? Often when we talk about temperature, we think about weather or thermometers and how hot or cold we feel, or we even think about like the weather forecast for the week. But what does it really mean physically for an object to be at 0 degrees or at 25, 30 degrees? What does that mean physically for an object? Well, it turns out that temperature is really just the average kinetic energy of the particles in a substance. So things with more kinetic energy have a higher temperature, and things with a lower kinetic energy have a lower temperature. So you can see in this box here, right, if these little particles in an object are zooming all around really fast, okay, so they have a high velocity, right, big velocity, that means they have a bigger temperature. But if instead you have particles that are just moving slowly, they have a low velocity, very small velocity, okay? And they have a lower temperature because temperature is the average kinetic energy of the particles in a substance. So we can also talk about another quality about things, and that is called internal energy. Okay, so we do have another kind of energy now, and internal energy is just the total motion of the particles in matter and their energies. So this means it's the kinetic energy and any potential energy that they have. Okay, it's the total energy. So it is proportional to temperature, right? Because the total energy will increase if the average is increased, but this is the total, not the average. And we use the letter U here to represent internal energy in equations, but we won't be learning any equations yet. So let's think about how things change temperatures now. So when you put an iced cup of tea on a table on a hot day, does it stay cold? Well, hopefully you answered that with a big, huge no. We all know that an iced cup of tea left out will warm up. We know that a hot cup of chocolate or coffee will cool down. But why does that happen? Okay, well, the fact that it will change temperature, this process is called thermal equilibrium. Okay, so anytime something hot cools down to match the room, or something cool gets warm to match the temperature, that's thermal equilibrium. So thermal equilibrium is just the process where the temperature of two objects in contact with each other will equalize, which means they'll become the same. So if you have your iced tea, and maybe your iced tea is really cool and it's at 10 degrees Celsius, and it's a hot summer day, and so the temperature outside is 30 degrees Celsius, okay, well, your hot cup of tea is going to warm up and change temperatures until maybe it's 29, okay, or even 30, because the temperature outside tends to stay roughly the same. Okay, so two things becoming the same temperature, okay, is thermal equilibrium. So this thermal equilibrium, this is the process that allows us to use thermometers, okay? This is the way the thermometers work. The idea is that a thermometer is so small compared to its environment, okay, right? So if you put it in your body, right, your body is a lot bigger than a thermometer, okay? Or even if you're comparing it to outside, all of the outdoors is much bigger than just a thermometer, okay? So the thermometer is so small that whatever its temperature is, it doesn't affect the temperature of what is being measured, okay? Or at least it doesn't affect it very much. But it becomes the temperature of its surroundings. And that allows it to expand, and we're going to talk about that in a minute, and rise or lower to the temperature of the material around it. And the other part of what makes thermometers work is the fact that matter expands as it heats up. And that has to do with the energy of the particles. The faster they're moving, the more space they need. And so things heat up and they expand, they get bigger. And that's why we have these things. These are called expansion joints, and you'll see them in bridges, and you even see them on the one that we drive to school on every day. So take a look out your window and see if you can notice them now. But these exist because the bridge will get bigger as it heats up, and it will get smaller as it cools down. And so if it was one solid piece, that could actually cause cracks in the road that eventually could make the bridge fall down. And so engineers have learned to build these expansion joints, and you can see all these little teeth here. What happens is the bridge heats up, those teeth will get closer together, and as the bridge cools down, they'll get further apart. And so it allows the bridge to change size without actually harming the bridge. And so it's able to remain stable enough for us to continue to use. So the key here, though, is that matter expands as it heats up. So you need to remember that things can actually change size. Okay, and this is true for all materials. However, water is special. One of the things, and this helps fish to live in lakes in winter and things like that, but water is one of the few things that for just a couple degrees will actually get more dense, so it actually gets smaller as it heats up, but then it follows the same pattern. So if when water goes from 0 degrees Celsius to 4 degrees Celsius, it actually gets denser before it starts expanding. Okay, so what happens in really cold places where water and lakes freeze in the winter is the water at 0 degrees, as it gets denser, the cold water will sink. And so normally, if something got colder, you would have all the solid pieces on the bottom. But because frozen water at 0 degrees Celsius is less dense than 4 degrees, and that's why ice floats. So ice is one of the few things that is less dense in its solid state than it is in its liquid state. And this allows fish to live in the winter in very cold places. So talking about temperature, there's 3 common units of temperature that we use. We have degrees Celsius, which is used everywhere except the U.S. We have degrees Fahrenheit, which is used mostly in the U.S., and then we have kelvins, which is pretty strictly used by scientists. And I just want you to know real fast, we use degrees Celsius, degrees Fahrenheit, but we do not say degrees Kelvin. Degrees Kelvin is wrong. We just say Kelvin. So Celsius is a very scientific unit for measuring temperature. It's based off of water's boiling and freezing points. And then 0 was set for water freezing, 100 was set for water boiling, and they divided up all the space in between by 100. Fahrenheit is a little bit random, but 32 degrees is set where water freezes, and 212 is where water boils. It was not based off of water, it was based off of a couple different things. And so it doesn't quite correspond to any one thing, and that makes it a little less useful than Celsius. So as we're talking about temperature, we defined it as the average kinetic energy of the particles. And so I've got a question for you. Since temperature is the measure of the average kinetic energy of particles, what happens if there's no kinetic energy? Okay, what would we have? Well, we would have no temperature, right? Which, if we said we had no temperature, we want to call that 0. Okay, but 0 degrees Celsius is where water freezes, and it still definitely has temperature. So that's how scientists came up with the idea of the Kelvin temperature scale. Kelvin sets 0 as the temperature where there's no kinetic energy, and they call this absolute zero. This is very, 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 very cold. Absolute zero is at negative 273.15 degrees Celsius. Okay, but to make things simple, because Celsius is widely used, they say it's the same unit distance as Celsius. So 1 Kelvin is equal to 1 degree Celsius. Just 0 is set at negative 273.15. Absolute zero is also extremely difficult to get to because there's no kinetic energy. Nothing can be moving, not even all the little particles in an atom. Electrons can't be spinning about their nuclei. And the closest we've gotten to absolute zero is 0.0000008, I believe. Okay, which is very, 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 very cold, but it's still not at absolute zero. So we can convert between all of our temperature scales by using these equations. Okay, Kelvin and Celsius, it's pretty easy because they have the same unit. So Kelvin is just equal to whatever the temperature is in Celsius plus 273. Fahrenheit is a little bit more confusing because they don't use the same unit, so we have this factor of 9/5, multiply it by the degrees Celsius, and then add 32, and you'll have Fahrenheit. You guys should have seen these equations before in other classes at this point, so I'm not going to go through examples of how to convert. The last final things I want to talk about is as we go into this chapter 9 and talking about heat, I want you to think about what does the word hot mean to you? What does the word cold mean to you? Okay. Well, in science, the words hot and cold don't have any value or meaning. They're subjective terms because they're based off of our perception, our feelings of temperature. But sometimes our perception is wrong. So I'd like you to think about this. Okay, if you have a block of metal and a block of wood at the same temperature, one of them will actually feel colder to you. We're going to learn about why this is and what property causes this a little later in this chapter. Okay, but I want you to realize that our feelings about temperature don't really tell us what the temperature is. That's why we created thermometers, so we can accurately measure it. And so it's really important to just get that idea out of your head that hot equals high temperature and cold equals a cool temperature. It may be right on average, but that doesn't give us actual scientific information. And the words hot and cold don't actually mean anything scientifically. So please take a minute to reflect on this and think of if you have any questions, write them down, and I will see you guys in class.